Okay, so now that we've talked a bit about electrons and we've talked about the structure of the atom, we're going to jump into how these atoms are organized on the periodic table. So a little bit of history. J.W. Dauberreiner, he put the elements into groups called triads. And he was able to see that these triads of elements had similar properties. And today, you'd actually see in the modern periodic table that these are elements that have now ended up in the same column. And he didn't necessarily know why they had the same properties. He only knew their atomic masses. But it turns out their electron configurations all end with the same thing. For example, lithium, sodium, and potassium here in this first column of the table, their electron configuration all ends with S1. And calcium, strontium, and barium, theirs all end with S2. And here, chlorine, bromine, and iodine all end with P5. So these, he didn't know it yet, but these ended up being in the same what we call group or family of elements. So this second person, he's the one that we really want you to focus on for test purposes. He's the most famous. He's sometimes called the father of the periodic table. There's an element named after him. I showed you guys a little video of this in class. So he put the elements in order of repeating properties based on their atomic mass, and he left spaces for undiscovered elements. And you may remember we saw a little TED Ed video on this. He actually predicted, you know what? We haven't discovered this element yet, but there's a blank here, and I believe that there's an element that goes in that spot, and here's how it's going to behave. He could figure out what its melting point probably would be, about how much it would weigh. So, brilliant man, putting the table in order like this. Now, it turns out that Henry Moseley, he's the one that actually put the table in order by atomic number. And so the table today, the modern table, is in order by atomic number. Not that it's not in order by atomic mass, because technically the atomic masses also sort of follow in order for the most part, as far as I know. But the thing is that the atomic number, since we're just adding another proton, another proton, another proton, this gives us a nice like whole number, element 1, element 2, element 3, rather than element 4.008, you know, if we're going by the atomic masses. So the periodic law says that when you arrange elements in order of increasing atomic number, their physical and chemical properties will show a periodic pattern. In other words, as you go from left to right across the table, their properties change from a metal that's very reactive all the way across to a non-metal that's very reactive, and then a noble gas. And then it starts over again. So there's a pattern, and each period or row kind of repeats that pattern over and over again. So today's periodic table is arranged by atomic number. The periods are the rows, and the groups or families are the columns. And then in each square, there's different information. Now, it really depends what table you look at. Some tables have more information than others. Some of them even have their electron configurations in the little boxes. But the ones we use in class always are going to have certain things. The element symbol and name are always going to be there. The atomic number is definitely on the table that we use, and the atomic mass is on the table that we use in class. Some tables are color-coded. Blacks are solids, reds are gases, and then blue is for liquid. And then again, some of them actually have the electron configuration. So if you look at this one, so sodium, this has the symbol, it has the name, it has the atomic number, and it has the atomic mass. And this one also adds in, these are the number of electrons in each level. So it really just sort of depends on the table what information is provided. And I know I'm zipping through this pretty quickly, but these notes are pretty straightforward. All right, so the columns, make sure you know that they are called groups or families. Some tables name them 1 to 18. That's sort of the modern way of naming them, is 1 to 18 from left to right. Some of them have specific family names. You really should just memorize this. So the alkaline metals, this is your first column. The older version of the table names these columns like 1A, this is 2A, and then these are all Bs. And then it comes back over here and it's 3A all the way over to 8A. That's more of an older version of the table, and these numbers kind of correlate to the number of valence electrons, actually. But the newer tables, and I believe the ones we're using in class, they basically just go straight across 1 to 18. So it's just two different ways. 2A, or group 2, this is your alkaline earth metals. So alkali metals, another word for something being basic, like a pH above 7, the opposite of an acid, is being alkaline or alkali. So that's where this comes from, alkali and alkaline. These form bases, in other words, things with a higher than 7 pH, the opposite of an acid, in water. Group 7A or group 17, all the way at the right before your noble gases. These are called your halogens. They tend to form salts. They react with metals to form salts. Halo means salt. And then group 8A or 18 on our modern table, this is our noble gases. So these are specifically named. Others are sort of named by the top element. So the oxygen group is the one with oxygen at the top. The carbon group is the one with carbon at the top. And again, the A columns are what we call the representative elements, and that's here. This is going to be 1, 2, and then 3 through 8 in the older version of the table. So you see the older naming system here. So these would all be called representative elements. There's actually another definition of representative elements that doesn't include the noble gases. That'll come up. But sometimes they are included as representative elements. These transition metals in the middle here, these are your B columns in the older version of the table, and they have some different behaviors than the representative elements, so that's why they're numbered a little differently. All right, now the next slide is going to talk about how this relates to electric configurations, and it actually makes more sense if I show it to you in this picture. So the first row of the table, the first period, is basically filling 1s. 1s1, and then 1s2 over here. Then the second row of the table is filling 2s, so 2s1, 2s2, and then 2p1 to 6. Then 3s is our third column of the table. Then starting with 4s is our fourth column, and notice, remember the order that they fill, it fills 4s, then fills 3d, and then it fills 4p. And that's why this row here, the D's, that's why it's organized this way, because it's organized in the order that the electrons fill. So 4s, then 3d, then 4p. Then if you remember, it's 5s, then 4d, and then, 5p. And then it started confusing myself. And then 6s, and then it comes down here and fills 4f, and it goes from there. So the table is organized. It's in order of increasing atomic number, but if you notice the way that the boxes are sort of organized together, it is in order of their electron configurations. And that's what this is explaining. So the periods, there's 7 rows, and they basically, each one is corresponding to a new energy level. And they're in order by the way the shells fill. Again, notice the periodic table here, right? So 4s, then 3d, then 4p. So like that. So that's what this is explaining. So row 1 starts with 1s, then the second one starts with 2s and 2p, row 3, 3s, 3p. Row 4, remember 4s, then this is where the D block starts, 3d fills, and then 4p. And then row 5 is up to 5p6. Row 6 is 6s, goes down to f and comes back up. We just covered this in the last chapter, so hopefully that makes sense. Okay, so they're also organized in classes. So 80% of the table are metals. All right, and what metals have in common? Several things. One, they're good conductors of heat and electricity. They also are solids, with the exception of mercury. It's the only liquid metal. Some of them do have very low melting points. They all have luster, or in other words, they're shiny. They're ductile or ductile. It means that you can draw them into wires, like think about copper wire, for example. And they're malleable. You can hammer them into sheets. You can bend them. They're flexible, rather than, say, being brittle where they crack. And these are some examples. Now notice how this doesn't look very shiny. If you were to cut the potassium, it is actually cuttable. Believe it or not, it's actually kind of soft. Inside, it would be shiny. But a lot of these tend to react with the air or the water vapors in the air, and they oxidize. They turn black on the outside. But they are actually shiny if they haven't, had a corrosion happening to them. So these are just some examples of different metals. Non-metals, on the other hand, this is your upper right of the table. Their properties can actually vary. Most of them are gases, but a few of them are solids, and bromine is a liquid. There's only 2 liquids on the whole table. Bromine is one, and the other one is mercury. Mostly they are poor conductors of electricity. They do not conduct electricity, and they're brittle. If you hit them with a hammer, rather than bending, they will actually break or shatter. And then metalloids form this sort of stair step between the metals and the non-metals. They show some properties of both. Some of them conduct electricity, some of them are a little bit shiny, but then they're also brittle. So they're kind of a mix. And these are the ones that are included. Sometimes some of these ones at the bottom are a little questionable. But if you look at the table, and this is your P block here, you can actually start your stair step right here. Boron is up here. And if you start the stair step and do this, it's pretty much everything to the right of that stair step. This is aluminum. That is not a metalloid. That's actually a metal. So I usually tell people it's going to be boron, then it's going to be this this second one here, 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 and then it's also these two on this side. So it's everything on the right of your little stair steps, but on the left, not aluminum, but the other ones that are on the left of the stair steps, if that makes sense. So that's the way you can identify them. Look for the zigzag line. A lot of times periodic tables will actually have that line kind of in bold. Electron configurations, the ones that are in the same group are actually going to end with the same thing. So everything in the first column ends with S1. So this is your S block here. This is your D block. F is below the table because it would make the table too wide. But actually it fills after, this would be 6S, then it fills 4F, and it goes from there. And then P block over here. Notice helium, even though it's up here, it's actually part of S block because helium ends with 1S2. We don't usually put it over here because it's not a metal. If you put it over here, and where the other things that end with S2 are located, these are all alkaline earth metals. But helium's not. It's a noble gas because its shell is completely full. Because there's only one S on that first level. So in 1s2, that's a full outer shell. Starting with level 2, in order to have a full outer shell, you have to have S and P full. So everything else besides helium, these all have 8 valence electrons to have a full outer shell. Helium only has 2. All right, and this is just showing what I just said. So notice how everything in our first column, our alkali metals, all end with S1. And then same thing with our alkali earth metals, they all are going to end in S2. And this just keeps going. Now the main groups, there are 4 main groups, the noble gases, representative elements. Now remember, this came up earlier and included the noble gases because it was everything in those A groups. This was like 1A, 2A, and then over here it was like 3A up to 8A. So that was all considered representative elements, but then others define it, so we wouldn't test you on this, but others don't include the noble gases. They're their own thing. So the transition metals and then inner transition metals. This is basically your F block. This is your D block. Noble gases are the far right, and then the representative elements are basically everything in S and P, not including the noble gases. So it's a little tricky. So noble gases, that's your 8A. What do they all have in common? Very stable, unreactive. They all have a completely full outer shell. So for helium, that's just 1s2. For every other one, it's S2p6, completely filled 8 valence electrons. So you look here, all completely filled outer shell. 6s2, 6p6, 5s2, 5s2, 5p6, 4s2, 4p6, etc. All completely filled outer shell. Representative elements, they are kind of a good representative. This is basically everything in S and P except the noble gases. Again, earlier I told you that sometimes the noble gases are considered representative elements too. But for purposes of this, it's these. So because these have their own special properties. Your transition metals are going to be D, your D block. It's a transition between the metal and the non-metal area. So it's everything in here. These were electron exceptions we talked about, how they wanted to have an exactly half half full D or a completely full D. And again, this is our Ds. And then lastly, our inner transition metals. These used to be called rare earth elements. That is our F block.